Welcome everybody to a short lecture on the vector form of Green's theorem. And remember that Green's theorem, the way we originally stated, says if we have a vector field, which I think of f of x and y as m x and y I plus n x and y j, then the integral over a closed curve C of m dx plus n dy is equal to the integral over the region that C bounds of dn dx minus dm dy dA. So we think of a C as a closed differentiable curve, a closed smooth curve, I believe this book calls it, which is orientable, and it's oriented counterclockwise. And so C is some closed curve like this, and it's oriented counterclockwise, and it bounds some region D. Okay, so that's the original statement of Green's theorem. And of course, the vector field F has to be C1 so that these derivatives right here make sense. Otherwise, the theorem doesn't mean anything. Okay, so the first way we're going to view Green's theorem in vector form is to think of F as a three-dimensional vector field with components m times I plus n times j plus 0 times k. So now I'm thinking of F as a vector field in 3 dimensions, which you can think of M and 0, okay? All right, and now what would be the curl of this vector field? So then the curl of F is ijk. It's a straight line, partial with respect to x, partial with respect to y, partial with respect to z of m and 0. And if you write that out, you have I times 0 minus n sub z, but m and n only depend on x and y. So you get 0 minus 0. And then when you look at the j term, you delete the row in the column with j, you get 0, and m only depends on x and y. So again, you get 0 minus 0. And then we get the k term times, look at that, n sub x minus m sub y. So the curl is exactly the term we get in Green's theorem on that right-hand side. All right. And now let's, so by the way, so notice when you write the line integral over C of f dot dr, what does that mean? That means the line integral over C of the vector field m n 0 dotted with r prime of t. So you think, the parameterization of the curve would be x prime, y prime, z prime, and then dt. And now we should integrate over the parameterization from, let's say, from t0 and to t1, okay? So notice that would be t0 to t1 of mx prime of t dt plus ny prime of t dt plus 0 dt. Okay, so that is exactly x prime of t dt we can write as dx, y prime of t dt we can write as dy, so this is exactly the same thing as the line integral of m dx plus m dy. Okay, so this notation right here is the same as this piece. All right, And that was one side of Green's theorem. Now we want to, and now we have the curl of f dot k, the curl of f is k times this term. So notice, rewriting Green's theorem, then we have the integral along the closed curve C of f dot dr is equal to the integral over d of the curl of f dotted with k dA. Because the curl of f is n sub x minus m sub y times the vector k. When you dot it with k, you get k dot k, which is 1. So this is exactly the same thing as the right-hand side that we had in Green's theorem before, okay? So one can view this as a vector form of Green's theorem. But it's not the only one we're going to want to look at. And before we go on, let's talk a little bit more about what this means. Okay, so before we go on, again, I want to look at this side a little bit, and now think about this. Now, this is the integral, or the line integral, of the tangential component of f along the curve C. Why do I say the tangential component? Because dr means r prime of t dt, and r prime points in the direction of the tangent vector. Okay, r prime is the tangent vector to the curve r of t. Okay, and now when you look at this right-hand side, what does this part represent? So this part is the integral of the vertical component of the curl of f over the region D. Okay, so Green's theorem says that the line integral of the tangential component of f along the curve is the same thing as the vertical component of the curl of the vector field along the curve. Okay. All right, that's nice, but what we, and that's one goal that we had, but we would also like a version for the normal component of f along C. All right, so let's see what we can do about that. Okay, so we know our curve C is parametrized by x of t I plus y of tj. Okay, for t between t0 and t1. Okay, and we remember from earlier in the semester that the unit tangent vector to C is x prime of t divided by the length of r prime of t times I plus y prime of t divided by the length of r prime of t j. Okay, and we also hopefully remember that the outward unit normal along the curve C outward unit normal along the curve C, yeah, is n, which will be y prime of t over r prime of t, length of r prime of t, minus times I, plus x prime of t, or minus rather, x prime of t divided by the length of r prime of t times j, okay? And you can check that that's a unit vector and a normal because it's orthogonal to the tangent vector. Just take the dot product, you'll see it's 0. It's sort of obvious, okay? So now let's look at, we wanted to get a version of Green's theorem for the normal component of f along C. So let's see what we can say about that. So suppose I look at the line integral of f dot n, which is the normal component of f along the curve C. And I'll look at that with respect to ds. So what is that? That's going to be the integral from t0 to t1 of f dot n, when I write it out in terms of the parameterization, times the length of r prime of t dt, because that's what ds is. We also remember that from much earlier in the course. Okay, so let's see, what is that written out? So when you take f, whose components are m and then you dot it with n, whose components are written right up in front of you, you see that you get m of x of t, y of t, times y prime of t over the length of r prime of t, minus n along the parameterization, times x prime of t divided by the length of r prime of t. So that's the dot product of f with n. And then we have to multiply by the length of r prime of t and dt, which I'll stick over here because I ran out of room. Okay. And now notice r prime of t is a common factor in here. It cancels with that one. So what we get is exactly the integral from t0 to t1 of m of x of t, y of t, y prime of t, minus n of x of t, y of t, x prime of t, all times dt. Okay. But y prime of t dt is dy along the curve, and x prime of t times dt is dx along the curve. So we could write that out as the integral over c of m dy minus n dx, which looks a lot like something that appeared in Green's theorem, not exactly because the m and n have kind of switched places, but you can apply Green's theorem to a line integral of this form. So now we apply Green's theorem. And what did Green's theorem say to do? It says the line integral gets replaced by the integral over the area that it encloses of, you look at the coefficient of dx and you let's start with, you look at the coefficient of dy and you differentiate that with respect to x. And then you look at the coefficient with respect to x and you take minus the partial derivative of that with respect to y. So minus n, and I take minus that gives me a plus, and I have to differentiate that with respect to y. And then it's dA. That's exactly what Green's theorem says in this case. But now when you stare at that for a second, you recognize, hopefully, that this is the divergence of f. Okay. Okay, so here's our vector form of Green's theorem the second way. So this is version 2. And it says that the line integral over the curve C of f dot n ds is equal to the integral over the interior of the divergence of f dA. Okay. And it's in that form that you'll see generalized completely when we look at the divergence theorem in a later section in this course. Okay, that's it for today's lecture. Short and sweet. See you in the next modules. Bye.